Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. A reminder that if you enjoy the show, please do consider supporting us through buying me a coffee. It really helps us to keep making the show. Today, I'm joined by Cuong Nguyen, who will be telling us everything we need to know about Detock, high-performance, multi-region transactions at scale. Cuong is a PhD student at the University of Maryland. Cuong, welcome to the show.
Thank you, Jack. I'm very happy to be here.
Great stuff. So let's jump straight in with some questions then. So tell us a little bit more about yourself and how you became interested in database research.
Yeah, sure. So I am currently a PhD student from the University of Maryland. And during my undergrad, I had the opportunity to work on a research project on time series data mining. But at the time, I wasn't sure whether I would pursue a PhD or not. So after my graduation, I started to work in the industry for a little over a year as a software engineer. And this is when I started to develop my interest in distributed systems and database systems. I want to learn more about them. And that was when I started to apply for a PhD and eventually ended up with my current advisor at University of Maryland, Daniel Abadi. And we are doing research in transaction processing.
So great. So let's have some background for the listener then. So can you maybe tell them about transaction processing and geo-distributed databases, which are what Detock is? So yeah, why do we need them, and what are the challenges that come with these types of systems?
Yeah, sure. So transaction is a very important concept in database systems. So it's the concept where you have either all of the operations in the transaction to be executed successfully or none of them would be successful. And geo-distributed database is when the database is spread across different geographical regions around the world. For example, you can have a database node running in a data center in the east coast of the US, another node running in the data center in Europe, and another one running in Asia. But eventually, you want to abstract away all this complexity and present the database to the applications if the database is running on a single node. The reason why we need to geo-distribute the database is in today's world, many consumer-facing applications have users located all around the world. And it has been common for these applications to require high availability and serve low latency requests to the users. These requirements are very hard to achieve if you only run your database in a single location. So, additionally, this kind of setup also makes the database more resilient to regional failures because you have data in other regions for backup. The biggest challenge to this kind of setup is that you can have very high network latency on the order of hundreds of milliseconds due to the fact that the database nodes could be very far away from each other. And this network delay will not only impact the latency perceived by the end users, but it can also affect the throughput of the system. For example, if you use locking for concurrency control, the network delay may cause the transactions to hold the locks for a lot longer, preventing all the conflicting transactions to make progress. And therefore, it will reduce the number of transactions that you can process at a time.
Awesome, cool. So yeah, we want these for like high availability and fault tolerance, but then obviously that comes with the trade-offs right there that we need. That comes with high network latency, and then like you said, it can degrade throughput if we don't get our scheme quite right. Cool. So with all these challenges in mind, then give us the elevator pitch for Detock.
Yeah, so Detock is a geo-distributed database system that uses something called deterministic concurrency control to move this high network delay out of the contention windows of the transactions. And therefore, it can achieve high throughput for strictly serializable transactions. But additionally, it also partitions the data across different regions. And it's take advantage of the localities of the workload so that users can just access data that is closest to them. And we also use an abort-free deadlock resolution protocol to reduce the latency of the transactions.
Awesome, cool. So you hit on a term there, deterministic databases. So what do you mean by this, and how does that differ from like normal non-deterministic databases, I guess, right? So yeah.
Okay, sure. So Detock is part of a line of research that involves this idea of using determinisms to speed up transaction processing. And the high-level idea is that so you would try to perform the necessary coordination among the transactions as much as possible before executing the transactions. And this way, you don't have to do these expensive coordinations during the execution of the transactions. in which a long delay might increase the contention window of the transaction. So for example, let's say in a non-deterministic database system, you might use two-phase locking for concurrency control, and you also want to replicate your data, right? But during the commit of the transaction, you have to invoke the replication protocol to persist the commit record. But this replication process will increase the lock holding time of your transaction and thus prevent other conflicting transactions to progress. Now, on the other hand, in deterministic database system like Calvin, which is published in 2012, you have an ordering layer at the very top, and every transaction will be ordered in this layer. And then every node in the system will then execute these transactions in a deterministic manner following this predetermined order. So by doing this, you have minimal to no further coordination during their executions. But note that to do this pre-coordination, we need to make an assumption that the transactions will be sent to the system in one shot. So unlike in conventional database system where you may make many back and forth trips to the database system, like you start the transaction with a begin statement and then send a couple of SQL statements and then finally send a commit to finish your transaction. In a one-shot transaction, you package all of these statements into a single request, and send this request to the system.
Awesome. Yeah, I've often wondered, whilst I've obviously been working in this area, how big of an assumption is that transactions are one shot and you don't have this interactive pattern of begin sending statements and then issue a commit or abort or whatever? I guess how big of an assumption is in reality does that reflect the way most applications are actually developed or not?
Yeah. So to my knowledge, first of all, in academic, I think one of the first papers that proposed this idea of using one shot for OLTP workload is the paper on HStore, and they argue that usually in OLTP workload you will have short transactions, and you usually know ahead of time what the code for the application would want to send to the database, so you can just package all this into a one-shot request. And in realities, I know of some systems that use this one-shot models like Tau from Meta. It's one example for a system that use one-shot transaction.
Nice, cool. So let's dig into the details of Detock a little bit more then. So maybe let's kick things off with give us a high-level overview of the system architecture. Then we can go into a few of the important features of the system.
Sure. So Detock is deployed across multiple geographic regions. And the way you can think of these regions is that the servers within one region are connected with fast network links, but the connection across two regions can be a lot slower. Now, for every data item in the database, we assign exactly one region, which we call the home regions of the data item. And by assigning the home regions for every data item, you effectively split the database into separate partitions across different regions. So there are two types of transactions in Detock, single home transactions and multi-home transactions. A transaction is single home if all of the data items that are referred to in the transactions have the same home region. And a transaction is multi-home when its data items are from more than one home region. Within each server, we structure the Detock process as a stack of modules. So first we have a forwarder module which is in charge of forwarding the transactions among regions. In each region, we maintain a local input log for the transactions. So we have a sequencer module that uses a consensus protocol like multipaxels to append the transactions to this log. Next, we have the log manager module that manages the local log, as well as the logs that are asynchronously replicated from all other regions. And then we have a scheduler module, which will create an execution module for the transactions in the log. And finally, the transaction will be dispatched to the workers, which will execute the transactions. And as you can see, this kind of architecture matches closely with the idea of deterministic database system, where you have an ordering layer on the top and then an execution layer after that.
Awesome, cool. I just wanted to touch on the replication there. So you've seen that data items have a home region. Every data item is like one distinct home region. Are data replicated across regions still? Just that you assign, I don't know, like you say you've got 3 regions and some data item X, and its home is A, is the A region. Is it replicated across B and C as well, or is it all within one region?
Yeah, so there are two types of replication happening here.
Okay.
So first you have synchronous replication, which is preferably done within the same regions or within neighboring regions. And this replication is used for fault tolerance in the case if a node in a region failed or the whole region failed. We also have another replication mechanism that is done asynchronously. So each region will asynchronously replicate their log to other regions. However, this asynchronous replication mechanism is optional, but we highly encourage the usage of this mechanism because it will speed up the processing of multi-home transactions, and it will also provide the possibility of snapshot read. So there are two types of replications in the system.
Awesome, cool. Yeah, another thing that sort of jumped out to me when you were describing the architecture there, Cuong, was how do I determine how does a user do I decide where to put certain data? How do I know to make my data item foo in this region? Like, is that totally down to the user to express locality of where it wants that data item to be?
Yeah, so we don't focus a lot on like the decision on where to look to place the data. It's mostly up to the application to decide on that. We focus more on the transaction processing aspect of the system.
Cool, yeah. Well, that's a good segue into the concurrency control protocol and this abort-free deterministic deadlock resolution protocol you mentioned earlier on. So, can you maybe illustrate how these two protocols work, and maybe do this by, I don't know, like you walk through a life cycle of a transaction, either a single home or multi-home. The floor is yours. Take it away.
Yeah, definitely. Okay, let me walk you through a single home, how a single home transaction is processed. Let's assume that we have two regions A and B. We start from a client sending the transaction, let's call it T, to a server in region A. The first thing that this server does is that it will extract the read and write set from T. And this can be done by static analysis of the transaction code, or if this is not possible, then we can send a read-only reconnaissance query that will perform all the necessary reads to discover the transaction read and write set. In this case, the read and write set would be speculative, and T might be aborted later if the read write set change between the time that we do the reconnaissance read and when we start executing T. And with this read write set, the servers can now determine whether T is a single home transaction or a multi-home transaction by looking up an index. And let's say in this example, we assume that T is a single home, so every keys in T belong to one region, let's say region B, right? Now T will be forwarded to its home region B, and then here it will be appended to the local log of that region. And at this point, the scheduler at region B will pick up T from the log and add T to the dependency graph. Okay, let's talk a bit about this dependency graph. Remember that we have the read and write set of every transaction at this point. So we can construct a dependency graph where each vertex corresponds to a transaction and an edge is drawn between two vertices if the two transactions corresponding to these two vertices both access the same key and one of them write to the key. If we assume that every transaction in our system is single home, it's easy to see that this dependency graph is a directed acyclic graph or a DAG. And you can find a topological order on this graph and execute the transaction following this order. Okay, so next I will talk about multi-home transaction. In our example, region A will asynchronously replicate its local log to B, and B will also asynchronously replicate its local log to A, as I mentioned previously. And so eventually, every region will have the full set of logs from all other regions. And let's go back to our example. Let's say T is a multi-home transaction. And once it is determined that it is a multi-home transaction, it will be broken down into separate single-home transactions. And these separate transactions will be sent to the respective region. So in our case, we only have two regions, A and B. So T will be broken down to two pieces, and these two pieces will be sent to region A and region B. And these two single home pieces will be, again, added to the local log at these two regions. these two regions then exchange their local log asynchronously to each other. So each region will have the full copy of the local logs, and it will have all the information that it needs for T. But now when you build the dependency graph out of this set of logs, you might see cycles, because you can have, let's say, chocolate T1, T1 and T2. T1 might be ordered before T2 in A, but T2 might be ordered before T1 in B. So when you combine these two logs together, you have a cycle in the graph between T1 and T2. And this is where we need our deadlock resolution protocol. The way that this protocol works is that it will determine a stable subgraph in this dependency graph. And this subgraph has the properties that it will never change as new transactions are sent to the system, because we don't want a race condition where region A see a graph that is different from region B, and then the two regions will resolve deadlock in different way, and they will arrive at different state of the system, and we don't want that to happen. So we have an algorithm to determine a subgraph that would be stable, and it will be consistent between the two regions. So once we know that we determine this subgraph, we will find all of the strongly connected components in this graph. So a strongly connected component is a subgraph where every vertex in this subgraph will have a path to all the vertex in the same subgraph. And this strongly connected component is like a generalization of the cycle to determine deadlock in this graph. So for each of this component, we will rearrange the edges such that there will be no cycle within this component. And this a simplest way to do this is just order the transactions by their IDs, and then you can connect them. You can connect the edge between them in a linear fashion so that they no longer have any cycle. This have to be done deterministically so that two regions agree on the order of the transaction within a component. And once you found all of the strongly connected component in the graph, you can find something called a condensation of the graph, which is you can think of each strongly connected components as a super vertex, and you construct them as to a vertex, but you retain the edges between them, the original edge between them, and what you end up with is another directed acyclic graph. And now on this graph, you will be able to find the topological order. So now you have two order, this topological order and the order within each component. And by combining these two order, you can find the total ordering between the transactions. And this order is deterministic across regions, and you can execute the transaction following this order to achieve determinism.
Awesome. So I'm just going to repeat this back to you to make sure I've kind of grasped what's going on. So we kind of gather all of the logs from everybody else basically, and we build up this graph. But the problem is the graph might have cycles in it because different people may have different transactions ordered in different ways. So the first thing we do is we'd find a stable subgraph across this, which is like everyone's going to agree that this thing is stable basically. Like, this is fine. But there's still going to be some other bits that maybe aren't. So they'll be deterministically ordered, like essentially by like their IDs. So you kind of have like, so everyone agrees, and you end up with these connected components basically, and then you can order the connected components. So you end up with this sort of overall total order essentially of transactions. Is that kind of roughly how it works?
Yes, you get it right. Yeah.
Okay, cool, awesome, nice. So once we have this sort of this nice bot-free protocol and everything. There's this other sort of concept you have in the system where you call them home movement transactions. So kind of what are these, and how do these differ from like your single home and multi-home? Are they like, what's the difference between these two?
Yeah, so remember that we partition the data across different regions across the world. So the reason why we do this is to take advantage of the localities in access patterns. So in the real world, data access pattern can change. For example, in a social network application, you can have a user moving from one continent to the other, but you want to retain the benefit of data locality. So you want a mechanism to move the data from one region to another. And these home movement transactions is one mechanism to do that without having any downtime. And the idea is pretty simple. So you can construct transactions that have a single operation that will change the metadata of the data item from, let's say, region A to region B. However, the lock managers have to treat these transactions a bit differently from a normal transactions, because you want to prevent the race condition where some transaction might see data belongs to the old regions, but some other see the data as belonging to the new regions. And this could happen during that data movement. And to do this, when we lock the data item, we do not only specify the ID of the data item, but we also specify the regions of the data item. And depending on where a transaction is located in the logs in relation to this whole movement transaction, we can determine whether or not to abort this transaction for assessing the wrong region.
Awesome, nice. So yeah, it sounds like as the user moves, the ownership of the data can move around the system as well. That's a really nice feature. Cool. So let's talk about some numbers then. So how fast is Detock? So tell us about your experiments and the setup, what you compared it against, and what you found.
Yeah, so we ran the YCSB workload in our experiment that is modified for transactions, and we vary the amount of multi-home transactions and the congestion level. We compare Detock with two other deterministic database systems called Slog and Calvin. And in terms of throughput, Detock performs either similar or slightly higher than these systems. But the metrics that we care more about is the latency. And we saw that most of the multi-home transactions in Detock is up to 5 times faster than these other systems. And it is easy to see why this is the case. So both Slog and Calvin need to specify one region as the default region, and they have to route some or all of the transactions to this default region. And you can imagine that clients that are situated far away from these default regions have to make this trip to this default region for global ordering before it can actually access the data from the regions that it want to access. And in Detock, thanks to this deterministic deadlock resolution protocol, we can completely eliminate this global ordering process. So the transactions can be sent directly to the regions that they need to access data from.
Awesome. Yeah. Did you measure the impact of home movement transactions, and was there any sort of experiments on those as well? Like how if you have a workload running whilst the class, did you kind of simulate or kind of model people moving around the globe and seeing how the impact on performance of those?
Yeah, that would be a very interesting result, but we unfortunately we didn't do that experiment. We only describe what the whole movement transactions are in the paper, but we didn't do any experiment on that. But that would be a nice experiment to run in the future.
Yeah, it'd be cool. It'd be interesting to see if that had any impact at all. I guess it'd be nice. Cool. Yeah. So let's talk about some limitations of Detock then, because it sounds amazing, but these things always come with trade-offs and caveats, right? So maybe you could tell us a little bit more about the scenarios, maybe in which that Detock performance is suboptimal, and just the general limitations of this approach.
Yeah. So as we touched on previously, so one limitation of Detock is that it does not support interactive transactions. And because we need one source transaction for deterministic concurrency control to work, this could be quite inconvenient because you lose the ability to interleave database code with the application code. But then again, we think that this is still a reasonable assumption to make, because you can see other systems like VoltDB or Tau that make the same assumption. Another limitation of Detock is that it's based on Calvin. And in Calvin, it uses a single thread to schedule the transactions. And this thread could be a bottleneck and make it harder to utilize the cores in a multi-core system. So it would be interesting to think about how to apply this same deadlock resolution protocol, but with other deterministic concurrency control that utilize like NVCC or OCC, so that we can get rid of this limitation.
Nice. Yeah, kind of on that then. So how does Detock compare to like other sort of state-of-the-art geodistributed databases, be that in either the academic world or in the commercial world. Just and when we've obviously been talking that there's Calvin and Slog, and then there's other sort of systems that I can't remember. There was one recently out of what was the thing called? It was like a HStore sequel. I can't remember what the system's called. What's it called? I'll try and find it while you're answering the question. But yes, I know there's other systems out there like ARIA as well, which is a deterministic database, which I know addresses some of the limitations. And this, when you were talking about the data moving around the system, this kind of ownership thing, it reminded me of a protocol called Zeus that I read a while back. So yeah, like how does Detock compare to these other approaches? Where do you position it in this sort of space?
Yeah, so we focus on comparing with other systems that support trio partition database. So we didn't really look into comparing with ARIA because it's more focused on single data center deployment. But we did compare with CockroachDB, which is not a deterministic database system, but it supports geo partitioning. And we found that when we increased the contention level of the workload, CockroachDB would have an increased rate of transaction abort due to deadlock. And this is because CockroachDB use two-phase commit and some sort of locking mechanism for the right operation in the transactions, and it have to detect deadlocks and abort the transactions to break this deadlock. And since the Detock does not abort any transaction due to the deadlock, it can sustain a much higher level of throughput. And additionally, Detock supports strict serializable transactions, but the highest isolation level of CockroachDB is serializable. But again, one caveat is that CockroachDB supports interactive transactions. It is still an amazing database system, but we believe that our assumption would not be too restrictive for OLTP application, and if the application had the characteristic that can be supported by Detock, then I think it's still a good choice for a database system.
Cool. Yeah, I mean the ability to, especially in a geodistributed deployment, right, of having no aborts is like a massive win, because the wasted work that goes for having aborts, and so no, I can see why it has a massive win there. The system I was thinking of that was recent, it was called Lotus. I don't know if you've seen that paper. It was a VLDB paper.
Oh yeah, it's a very recent paper. Yeah, I have that paper, but I think Lotus again only consider the case of a single data center, single region deployment.
Right. Okay. Yeah. So they haven't gone geo-distributed.
Yeah.
Cool. Yeah. So awesome. So what's next on your research agenda for Detock then? So what's the next steps?
Right now, I'm working on a different project unrelated to Detock. So we don't have a specific plan for extending the research on Detock. But some of the ideas that I found interesting is, as I said before, to see if we can combine different deterministic concurrency control protocol with this deadlock resolution protocol, so that we can avoid any current shortcomings of Detock.
Nice, yeah, because I guess the University of Maryland is the home of deterministic databases, right? Like it was your advisor's original idea, so I guess there'll be more research to keep coming out of it on this sort of topic. So now I look forward to reading that. Great stuff. So yeah, so kind of again more generally sort of speaking here, as a software developer, data engineer, DBA, how do you think I can leverage the findings of your research, and kind of what impact do you think your work with Detock can have?
I guess one way to leverage this research is if you want to build a new database system, and if your requirements match with the transaction model that Detock can work on, then certainly there you have this new option for your implementation. Or even if you have a specific problems and it happens to match with the problem that Detock is trying to solve, then you can use the techniques presented in the paper to solve your problem. And we also open source our code, so you are welcome to reuse the code in your work.
Awesome, nice. We'll drop a link in the show notes to that, so the interested listener can go and find that for sure. Cool. So yeah, I mean, obviously, whilst you've been working on Detock, has there been anything that's jumped out to you? Have been like, oh, this is like the most interesting thing I've learned while working on this project?
I think most of the things that I learned was related to the software engineering aspect of like when building a system. And one I think I got two big lessons that I learned from this project. And one is you should instrument your code with observability tools early on. It helped a lot in finding performance bugs and just generally understand your system better. I didn't do this in the early stage of my project, so I have to spend countless time trying to figure out why something was too slow or why something is not behaving the way that we want it to be. And the second lesson is that cross-region requests in AWS are very expensive. So in my first few experiments, I was very generous with sending cross-region messages across regions, and I ended up with a quite hefty bill. And my advisor wasn't very happy with that. So I have to be more thrifty with that, and that brings down the costs of the experiments.
Yeah. It's very, on the first point you made there about the observability. I mean, I've fallen into that same trap before as well, and you just kind of you think, oh, I won't need it's fine, just hacking away, developing, and then all of a sudden you're like, oh shit, I need to figure out what's going wrong here, and then you've got no way of observing it, and it's yeah, it's cool. So yeah, I mean, kind of maybe loosely related to that then. Was there like a few things you tried along the way with the development of Detock, or maybe the idea or the actual implementation, and things that failed, and yeah, kind of maybe some war stories about this process you went through with Detock?
Yeah, so I think that the only thing that we tried a couple of times is the implementation of the deadlock resolution protocol itself. In our very first revision, we use a single thread, a single graph that is shared between different threads. And this is a very bad idea because every time you want to modify this graph, because in our protocols we need to rearrange the edges and all that, you have to acquire lock on this graph, and that's just bring down the performance of the whole system. And in the end, we end up with an implementation where each thread, actually there are only two threads here, that will build their own graph. And so they don't have any contention over the entire graph. And they will share the information about like what to change on the graph by using a message queue.
Okay, nice, cool. Yeah, I see. So just sort of, I guess, you mentioned it a second ago about that you're no longer working on Detock. You're on a different project. Maybe you can tell a listener a little bit about that project and maybe something about your other research.
So as part of the research on deterministic database system, we are working on a project where we investigate the practicalities of this deterministic database system in real application. And we do this by looking at the code of a bunch of open source projects on GitHub and just study their transaction code, write down like what match with the assumption that we need to make in deterministic database system and what not. And the second project I'm working on is it's another geo-distributed database projects, but it's not a deterministic database system. But we look into supporting geo-distributed transactions on existing single node database system.
Nice. So is that sort of what are these systems you look at? Are they like cloud-based systems you're looking at, and like kind of, I don't know, taking something like Aurora or one of these systems?
Yeah. That's also it's actually Aurora. It's actually the Aurora light architecture.
Okay, cool. Yeah, because I mean, sorry, continue.
Yeah, because Aurora's right now is really deployed in a single region. So we want to take it a step further and see if we can support geo-distributed transaction for this kind of systems.
Nice. And obviously Aurora as well is like single writer, right? You only have one node.
Yeah, exactly.
Right. So it's sort of like, can you make this multi-writer, and okay, so yeah, no, there's a lot of, I read an interesting paper at Cider actually. I actually had Tobias on the show who talked about that sort of stuff. But interesting to see how that project comes along. Nice, for sure. Cool. Yeah, great. Yeah, so I've got just two more questions for you now, and the penultimate one is tell me a little bit more about your creative process. So how do you go about generating these ideas and these really cool projects you work on, and then actually like filtering out the ones to pursue? So yeah, how do you go about doing that?
Yeah, so as a student, I'm still figuring out myself, and obviously, my advisors is a great source of ideas and things that I might be able to work on because he have a broader view of what is going on in the industry or in this area. But one approach that I am experimenting with is to look into the gap between research and what's happening on the real world and ask what are the obstacles that prevent this research to be applied to the real world. And about selecting what projects to work on, I try to evaluate the implication of solving each of these problems and then choose the one that would make the most impact. Yeah.
Nice. That sounds a really nice process. I can see how that works. It's really cool. Awesome. Cool. Yeah. So it's time for the last question now, the last word. So what's the one takeaway you want the listener to get from this podcast today?
A key takeaway from this work is deterministic concurrency control provide a framework for minimizing the overhead of coordination within a transaction. And this work on Detock once again highlights the viability of this framework in improving the performance of geo-distributed transactions. And additionally, I believe that there are still more opportunities to explore within this framework. And I hope to see future work that addresses any current limitations of the frameworks, as well as works that would try to integrate the techniques from this framework in the real systems.
Fantastic. Let's end it there then. Thanks so much, Cuong, for coming on the show. I've really enjoyed this conversation. If the listeners are interested in knowing more about his work, we'll put links to everything in the show notes. And again, a reminder, if you enjoyed the show, please consider supporting us through buying me a coffee. And we'll see you all next time for some more awesome computer science research.